them look like elongated structures, right? In the elongation itself, some of them have more structured features which are present. So the first thing you would have done is that you would have counted the number of objects. Second thing you would have done is that you would have done classifying them based on the appearance. Okay, this is I'm saying simple things, whatever you can do. Third thing you could have done, I think it requires a little bit of staring and this thing. You would have said that this looks redder in color. Some of them are looking greener or bluer in color. So first thing you would have said the number of objects. Second thing is the morphological classification. Third thing may be related to the color. Color or this can be, okay, that's what you would have done. So beyond this, what you can do? You cannot do much more than this because of two problems. Okay, third thing you would have done again is that even if point-like objects are there, this is very faint, this is very bright. So you would have said, if I take a photograph of the sky, deepest photograph of the sky, I will find different morphologies, I will find different brightness, I will find different shapes, I will find different colors. That's all. For example, if you take brightness, you cannot conclude an object which is bright, whether it is intrinsically bright or it is bright because it is close to me. For example, if I ask you, which is the brightest astronomical source you know, your answer will be sun, because it is close to us. But if you ask intrinsically, is this the brightest objects in the universe? No, right? So this problem is there. So brightness, whatever you are talking about, brightness has two elements. One is that how intrinsically, how much energy per unit time it is releasing. Second thing is that whether the source is closer to us or not. Okay, fine. So you cannot decide, how do you know whether something is close to us or not? You have to find the distance. With this kind of picture, you cannot find distance at all. Okay, that is the first problem. Second problem is even the shape. For example, this looks like, shape is like this. So imagine if I show it to you, you see that it is like a linear kind of thing. I keep on pushing it further and further, and I ask you to look at it with your naked eye. At some stage, you will not be able to distinguish this thing, right? It becomes so small, you will say there's something in black. So that could be the case here. One of these guys, which you are seeing here like a dot, or one of these faint ones which is clearly appearing like a dot, if you go and take deep picture, you may end up finding all the grand structures in it. So clearly, observationally, it is very difficult for us to make any progress beyond taking pictures. Okay, this is the problem. Let's narrate this problem clearly. Observable universe is a 2D projection. This we agree. This is the problem. Because when you take a picture, you are taking a 2D x, y, and location, right? X, y coordinate, you can look at the location. That's it. You can measure size. Size means like you can say whether it is small or bigger. You can measure brightness. These are the two things. The third thing which you can measure, if you don't do only images, is what is known as Doppler shifts. What you do is that for each object, now you can do one more thing. Light is coming from that object. You can pass it through the spectrograph, and that light will be split into a spectrum. And if you can identify features in the spectrum, which is like emission lines or absorption lines, and you can ask the question whether the wavelengths of these lines coincide with what we expect from the laboratory wavelengths, you can calculate relative velocity between us and this object. This is known as Doppler shift. When the object is moving towards you, what will happen to the wavelength? Wavelength will shift towards blue or red. Blue. So you know that. So the first thing is that you can take a picture. Picture will give you these two quantities. You can take a spectrum. Spectrum will give you the velocity. Okay, these are the measurements one can do. Size and brightness can be used to get the 3 dimension, right? This is the problem. For example, if I declare now all objects in the sky have the same brightness, intrinsic brightness or intrinsic luminosity. all objects emit same amount of light per unit time. Then you can reconstruct the depth. Then you will say that when an object is faint, it is far away. When an object is bright, it is closer to us. So these are known as standard candles. What are standard candles? In the case of standard candles, you expect the amount of emission per unit time or energy per unit time to be constant. If you find such objects, you don't need anything. You just take a picture. If the picture shows that object is closer to you, if the object is faint, you will say it is closer to you. If the object is bright, it is far away from you. But standard candle means what? We don't know. We cannot give bulb of 30 watts bulb to everybody and go and stand all over the place. So you need some unique physics, irrespective of whatever is the condition. When the physics is operational, it emits energy per unit time at a constant rate. So this you have to figure out. But of course, this is an idealized situation. We cannot say that all sources can have same brightness. It is rubbish, right? Because we cannot say that all human beings should have the same weight and height. It cannot happen, right? So that is the first point. So size and brightness can in principle be used, but it has to be used with care. That's the problem. No standard candles. Wavelength shift can be a useful proxy. This is what I am going to highlight to you, how you can use wavelength shifts as a proxy for measuring distances. So we will focus on this today. Okay, it is interesting, right? If you want to study about everything, you would have already heard that astronomers have found out universe has started from a Big Bang. Astronomers are doing all sorts of things. They are discovering a galaxy which is just very young. The light from that object takes billions of years to come to you. How do you know all this? Right? It's a conspiracy, and also one can call it as cosmic coincidence, because there are certain physical things which helps us find various quantities. Okay, let me give an example of how to find the distances based on velocity. Okay, so you know the well-known example. We will do that. So if I take sun and you take a planet which is going around, okay, for some reason, sun's mass is known. We will see how to do that. Suppose if you know that you know the mass of the sun, it will be denoted like this. If you put a dot and a circle, this is called sun. This is a representation of sun. If you put a circle with a plus, it is for Earth. Okay, you remember that. So if I know this, Kepler's law tells us the orbital velocity will be inversely proportional to the distance. Correct? So this is just an example. You will be able to find if I say that there is a planet which is going around sun with velocity v, right? Or it goes around the sun once in so many days, and I give you sun's mass 2 into 10 to the power 33 grams, you will be able to measure the distance. So this is the idea behind velocity being a proxy to distance. Okay, we have to see how you can do this, which means that in astrophysics, all distances will be measured in a particular context, which means that you will have some idea of what to do. Okay, so now you can also see how can I do this problem starting from scratch, in the sense that okay. So now let me I will go through some of this. We will systematically start from measuring distances in planet scale up to cosmology. That's what we will do in this class. Okay. So astronomical sources, in principle, how do you define or classify them? Unresolved point sources like stars, quasars, or QSOs, you will hear them in a sequence of lectures which you will have in coming weeks. Unresolved point sources mean these objects looks like points, and in any images you do, and you are not resolving their internal natures. Resolved objects, basically there are two kinds of resolved objects you will study. One is that ionized gas in our galaxy itself. If you take pictures, you would have seen beautiful pictures taken by Hubble, Horsehead Nebulae, this, that, and all. These are extended objects, extended regions, which are pumped or which are ionized by stars in them, and they emit radiation, and you see them in different shapes. And these are excited gas which is present in our galaxy itself. Other set of extended objects are galaxies which are far away from us. You see the full galaxy, and they look like extended objects. Okay? When you consider gas, which is very important, you have to worry about when you are talking about astrophysics. Most of the time you think that stars, constellations, because that is what skywatch things are doing, and they constitute very little amount of matter in the universe. Most of the matter in the universe is not in stars. Right? If you really want to understand where the matter in the universe rests on, you have to worry about gas. In fact, there is additional component which people will explain to you, known as dark matter component. I don't want to introduce them here. So the gas can be cold, warm, and hot. Gas means in general, it can be of any kind of matter. Ionized plasma, neutral gas, neutral molecular gas, whatever it is. Okay? So let me start with how do you do distance, basic distance measurement. This is what is known as distance ladder. We will start with the basic distance measurement one does. The first measurement is very simple. This is the measurement of distance to Venus. So Venus is the nearest planet to us. So what you basically do is that you take a laser beam when both Venus, so you imagine now there are two orbits here. So you are here. Suppose if you happen to be aligned at some stage, you can just shoot laser beam. The laser beam comes back, and you find out what is the distance between, what is the time taken between the sending of a pulse and arrival of the pulse. That, assuming that the propagation is happening through speed of light, and there is no delaying medium which prevents, which there is a refractive index can be ignored, you can measure the distance between Venus and Earth. Now, if you know how long Venus takes to go around one circle, you know that can be written in terms of Kepler's law, right? So you know how long it takes one rotation, you call it as distance r. And the second thing, you can take it the same thing for the Earth. It will have r plus this distance delta r. So you have two periods, and distances you can write down as r and r plus delta r. Delta r is known to you, then you can calculate r. Okay, so this is a simple method. Here it is very interesting. You don't have to even know what is mass of sun. You can solve for it. Because if you know the distances and periods, you can solve for this one. So this is basically, now if you see all the cosmological measurements we are going to do, you know, if I ask you what is your height, you will tell something 1 meter, so many XX centimeters. So this is based on a scale, right? Our height can be different if the scales have changed. The basic scales which we are going to use in this thing, it depends on how accurately you measure this distance. So this distance goes by the way you measure whatever you call Doppler measurement of speed, right? So you can now, having obtained these two distances, you can find distances to various planets just by using this Kepler's law itself. So I will not go into that. So you understood the first measurement you are doing is related to what we call as Doppler echo technique. We just send it. So second thing, so this way, what we have done now, our measurement to our distance of Earth with respect to Sun is very accurate. The accuracy of that measurement will depend upon how accurately you measure the time of arrival of the pulse after the reflection. As you keep increasing the Venus measurement, better and better, and orbital corrections, we are assuming orbit to be perfect circle, it need not be, there can be small ellipticity. You can do all these things, and that will give you the distance between us and Sun. This is of the order of 10 to the power 13 centimeters, 1.5, 10 to the power 13 centimeters. Okay? Now, having found the distances between planets, the next question we are going to do is that can we measure distances to nearby stars? The way it will be done is the following. Suppose you imagine that this is Sun and this is Earth which is going around. Okay? In January, the Earth is here. In July, the Earth is going somewhere else. And you can assume there is a star, which is nearby star, which is here, and these are very far away background stars. Okay. So what you do is that when you are here, you take a picture of this star. What you will find, your angle is like this. When you take a picture, the star will be here. These stars will be in the background. So you will find out what kind of background stars are there. This star will be embedded in this region. And in the next time, when it is in the other end of the thing, you make a picture. That time you see some other background. So given, assuming if these star backgrounds, if these stars are not moving within 1 year's time scale, which is true, not that stars will move all over the place, like you are not seeing like this, right? Any movement you are seeing, it is because of Earth's rotation. Stars on their own will not rotate. For example, if you fix separation between two stars, they both will move like this. But if you come to the next day and ask whether the separation has changed, it will not change. Okay? So what you can do is that you can measure the angle P between, so you can measure the angle, this is 2 theta, and you can calculate half angle of this, and you can do some trigonometry, simple trigonometry to calculate this distance, because this distance is known, this is not known. Okay? If you do tan theta of this angle, theta can be, theta is measured, tan theta or sin theta, whichever you want, you can find the sides. So we are interested in finding D. So you will do tan theta to this, and you can find out what is the distance. So this distance measurement is what is known as a triangulation measurement. So this is how you measure the distance to different stars. Okay. Now, what are the requirements for this? There are 2 requirements. Requirement is that the star should be closer to us. So that's it is like this. If I keep this pen, I look from here, I see these guys. If I look from here, I see this your group, right? If I keep it very far away, it's not going to be very different. You understood this point, right? That means this technique can be used only to a nearest set of stars. You cannot use it for very far away stars. Okay, you have to use closer to you. That is the first requirement. What is the second requirement? Second requirement is how accurately you measure this distance now depends on 2 quantities. One is that how accurately you know the distance of Earth from Sun. That depends on this laser technique, whatever sending echo techniques. The second thing is that how accurately you can measure theta. So, which is important. That means I should be able to pinpoint the location of the star as accurately as possible. So these are the 2 bottlenecks. Suppose I say that my accuracy is not very good, that means my distance measurement will not be very good. So considering all these things, what we know now is that we can measure this using this technique. We can measure up to, nowadays we can measure up to 2.5. So you measure up to 1,000 or 1,20,000 stars, to which you can measure the positional accuracy at 1 part in 10 to the 3, 1 part in 1,000 arc second. Arc second, you know, now it's 1/60th of a second, or theta in seconds, or whatever, degree minutes, right? Arc second, you know, that's what I'm saying. So this is how you measure distances to stars, but how many stars you measure, even if you give little bit leverage, you say you will measure point or distances for 2.5 billion stars. You will say, wow, it's too much, big number. But how many stars are there in our galaxy? They are in billions, not millions. So this is not good enough. It is good enough for us because the number is very large, but it is not good enough for us to map the whole distances to whole universe. So you understood. First is we did this measurement with lasers. Second thing is that to set off about this many stars, we measure them based on how accurately we can locate them and how accurately we can measure angular separations between 2 extreme ends of our orbit around Sun. Okay, so this part is, till now we have not done anything. These are pure measurements and geometry and whatever we know about the light propagating in the free space. These are the things we have done.
Like the background has to be fixed, right? The background star. like after 6 months, the Earth will be split side at the back. So how do we determine the background?
No, but this is extreme point. So this is extreme point, but actually you will not be shifting so much. So each object you have locations. You will give locations. You can say X and Y or angular scale. You can give locations, and you know the separation between them. Then you can calculate which angles can be calculated, right? If you say, if I sit here and here, I can find out what should be the angle so that I am looking at this star instead of looking at this star. So you can do in an angular coordinates you go and you can just measure what is the direction in which my light is going or my what you call line of sight is going. I take an arrow and find out what is the direction in which I am going because I know the locations of this star. That will give my angular location of the pointing. Now I find angular location of some other pointing. I can find the angle between them. For example, if I give you two stars, you can find what is the angle between them. Okay? You imagine like that. But here only difference is that we are not measuring from the same place. So it will cross like this and that angle is what you will measure.
So how will we know beforehand that if it's a close or not? The star is close to or not?
That depends on the accuracy at which you can measure the source itself. For example, I gave you, just now I told you, if I look like this, so if I look at a star, some stars for it the background is changing, some stars are not changing. Then you know which is closer to you, which is not closer to you, right? That's the simple way of putting it. So these stars will, depending upon where from I am looking at, these stars will shift with respect to the background star. All other stars will preserve the locations. These stars will appear as if they are moving around. They are not moving. It depends on your angle. Okay? So that's how you can do it. Convinced or not? Huh?
Little bit better.
No, I think little bit.
Because it will depend on the observation how we are doing. We have to observe it very nicely to see that if it's moving or not.
No, only you have to do 2 times. You have to do observations. One when you are here, another time when you are here. That's it. You don't have to observe all the time. The next thing, now we have to go to some kind of physics to understand, but I will not explain the physics here. Then you people will learn it next lecture itself when somebody teaches stellar evolution. You will learn these things. But I will teach only, I am very single focused on measuring distances. So if you go and look at any direction and take stars, you identify stars in the image. Stars means point sources which are appearing like points in the sky. And we said we can do 2 things. One is that you can measure the brightness. Second thing is that we can measure the color, whether they are red or blue or whatever. So what is plotted here is brightness. What is plotted here is the color. If some object is blue or some object is red, you will do it. So ideally what one expects is that you expect if you take such a plot, you take all the stars in the sky and you plot them in this plane, it should be randomly distributed, right? The plane should be completely occupied by points all over the place. So this is what you expect. In that case, if that happens, then you will say that there is no relationship between how bright the star is and what color it has. But what one finds is that you find that the stars don't occupy all the space, they occupy in a very specific regions. Okay? Specific regions is that there are regions where you find something like a inverse relation between brightness and color. Very bright objects are bluer in color, very bright stars are bluer in color, and fainter stars are redder in color. You see this kind of thing, and there are some other stars which are on the other side. Okay, so this is very interesting. So there are 2 ways of understanding this plot. You say that in creation itself, somebody has created them to fall in this particular place only. There is some physical reason why these stars are here. Means like I create somebody, that person will be bright forever and blue forever, or that person will be faint and red forever. That is one way of looking at it. Another way of looking at it is that there is a sequence in evolution. For example, like what happens to us. When we are born, we are very small. We can't even walk, we can't even turn, like we can't even speak, we can't even see things. During the evolution, you will become big and all, and you will be very youthful and all. Later on, you will become old. Again, you cannot walk, you cannot see, you cannot speak and that. So this is the sequence. So you can say that this could be sequence also, in the sense that if you are capturing a population, you are capturing a population over a wide range of age. It's going through a sequence of evolution. In that case, a snapshot. For example, this is what will happen. Huh? You go to Pune Central and just take a picture. You will find a kid going in the tram. You will also see old person sitting in a wheelchair. Maybe best place to take a picture will be airport. You will see them all. And you will see some young kid holding a parent's hand, vice versa. So if I take a snapshot there, again you can say that population have this kind of thing. Either they are small and forever they will be small, or you can say that this is the sequence. Okay. As far as as far as stellar evolution is concerned, this kind of shapes depends on some physics which is known as evolutionary sequence itself. This is what is called stellar evolution. You will study them. But I will give a very brief understanding of what it is. Then you will see that you can carry on further with this. So what happens here is that when stars are emitting light, you will be told that the stars emit light by burning hydrogen into helium. So 4 hydrogen atoms will produce 1 helium, and the mass of 4 hydrogen atom and mass of helium atom are not same. There is a slight difference. If you add all mass of 4 hydrogen atom, it is not equal to the helium atom. The extra mass is what becomes energy. Okay. So now you know that. So what happens is that it is a very slow process. Bringing 2 hydrogen atoms together itself is very difficult. When they come and join, and to produce helium, they have to go through a lot of steps. First hydrogen to deuterium, deuterium to 3 helium, 3 helium to 4 helium. So you will study all of them. But the point I want to say is that hydrogen has a characteristic amount of radiation emitted per unit mass of gas which is going through the nuclear reaction. Okay. So this process, when it happens, it goes on for a long time. Okay. If you want to appreciate this process, what is the difference between hydrogen and helium? Crucial difference. Ready?
Helium is more daily.
That is fine. In nuclear sense. Sorry? Yeah. So hydrogen has a proton, helium has a neutron. So can I simply combine 4 hydrogen and say become helium? Will it be possible? So what should I do? Louder please, nothing. What did you say? No, there is no bombardment of neutrons. This is purely hydrogen is present, right? How do I do it? So I need to somehow convert a proton to a neutron. Is it possible or not? But how long it will take for it to happen? Can I do it just like that, or it is a slow process? Why?
Repulsion.
Sorry?
Because of the repulsion.
No. You are converting only. There is no. I have a proton. It becomes neutron. What should I do? I have to do something, right? So you have read this or no? There is a simple way of doing that. What is that? Three neutron and proton are related by some decay. No? You don't know. So will it happen inside an atom? So that is the problem. Okay, I will leave it abstract like this. You ask person who is teaching stellar structure to explain this for you. You have realized that it is not very easy for converting a proton to neutron. It takes some time. A characteristic time can be of the order of 10 to the 7 to 10 to the 8 years, depending upon what density you are dealing with. Okay? So there is something called weak interaction cross-section you have to worry about. You have to convert this. It's like a quantum mechanical problem. I will leave it like this. That means even if I bring 2 hydrogen atoms or 4 hydrogen atoms together by some means. To make this into helium, I need to wait till a proton becomes neutron. This is the problem. So that's why hydrogen burning will take place for a long time, because I cannot burn hydrogen very quickly into helium because of this problem, this bottleneck. I have to convert. So it is a slow process. Then you will say, if it is a slow process, how do I generate energy? But you know, nuclear reaction is the best way to generate huge amount of energy. We need little bit mass only, and you will produce enough energy. This is what happens. So what happens in the lifetime of the star, most of the time, star will live in this space where it is trying to convert hydrogen into helium. This is what your sun is also doing. So they say like that, exactly like that. They will have the same color, they will have the same luminosity for quite some time. Okay. Only when hydrogen fuel is over, they will go to burning helium and all. Afterwards, there is no problem. Because once you create helium, you have enough protons and neutrons. You don't worry about converting these nucleons species, right? You can simply join them. So you understood this. That's why all the stars are remaining in this particular range. They are remaining in this particular range because they are fixed. They are unable to move. They are unable to change their luminosity. They are unable to change the color because the process of converting mass into energy is fixed, and it is a slow process. Okay. So if you want to see the analogy, again, if you go in the sky, you can see in Google Maps sometime. If you take a picture of Pune-Mumbai highway, where will you find maximum cars? You take a satellite picture. Where will you find? There are fixed places you will always find. There are few places you will find once in a while. The fixed places where you will find crowded cars is the toll gate. Because there is a slow process, everybody has to go through that process. So the speed by which the car will pass through that region is fixed. So it cannot be 80 km per hour. So if you take a photo, you find crowding there. The crowding there is decided by some process which is related to money collection. Crowding there, crowding here is fixed by the process of hydrogen burning. So this goes by the name main sequence. Okay. Okay, one more place where there will be crowding will be when there is an accident and you can't move. Okay. We understood this. So now, just interesting point. I will not do this part. You will hear from the interesting point is now what you can do is that you can take. Suppose you see a collection of stars are there. These are called clusters. So there is a collection of stars in one region. There is another collection of stars in other region. What you do is that you go and look at the color and luminosity of these stars and you plot them. What you say is that they live in a straight line, roughly. The interesting point is that whether you look at them, you call it as 1. You look at them, you call it as 2. If this is for 1, the second guy will be somewhere here. 2. What was found is that this slope, the slope you are finding between color and luminosity is invariant. Invariant means it doesn't depend on where we are looking at. Why this is lower compared to this is because of the distance only. If one is closer to you, so it appears brighter. Another is far away from you, so it appears fainter. So what you can do is that you can adjust the distance, because this axis is what I am plotting here, what is known as magnitudes. I have not introduced them to you. Magnitude is nothing but, it's a definition. Magnitude is one way of looking at it, but if you know the flux of the source, magnitude and flux are related by this relation. Okay. So here what I am plotting is absolute magnitude. Absolute magnitude is the equivalent of luminosity of the source. So if I want to have luminosity, I should know the distance of the source, because flux is what I measure. Luminosity is the intrinsic emission per unit time, that is 4 pi r square times the distance. 4 pi r square times the flux I am measuring. Okay. So what we do is that you know one cluster for which you found the distance. Suppose you have them. Then you have some cluster which you don't know where it is. You assume your distance to be different, and this guy will start moving up and down, depending upon what distance I am assuming, because it's an r square dependence. When this line goes and sits on this line, you can actually find the distance. You understood? But the other way of saying is that if I plot a relationship between color and brightness, this all follow the same. So here is an example. Red points are from some group of stars. Black points are from some other group of stars. And you can see, you can overlay one on top of another. They exactly follow the same curve. So this shift, amount of shift you are giving in this direction, this will be related to the distance which you are going to assume to this. Okay. So now, how do you know this? So that means you should know distance of one star cluster. Then you will be able to measure distances of several star clusters. Okay. So this is one of the examples. I just jumped a bit. Let's go back and see what are we understood. We know distances of all the planets. We know distances of the nearby star. If you know distances of group of stars, you can find out distances of all sets of group of stars by assuming the main sequence is more or less same because it is governed by a simple physical law, which is time taken for hydrogen burning to happen. That's the point. So you understood this, right? Now, we can also do a few more things which will allow you to learn the things. Suppose what is plotted here is the 2-3 scaling relation I will show you, then we will join them to build a relationship. Another thing which is found, which is interesting, was if you take the luminosity of the star, if you know how bright a star is, and you plot against mass of the star. Now I have not told you how to measure the mass. Who will do it? Okay, wait a minute. So these 2-3 steps are very important for us. If you do it, first thing you notice is that mass of the star and the luminosity, they are tightly correlated. You see these points, these are red points are measurements. The line which is passing through is basically a line you have is the fit to this. So it can be with a power law, right? You see that mass and luminosity are related. So you can actually write down mass is proportional to m to the power -3. Okay, sorry, okay, I will come to this. Okay, 1 minute. Luminosity is proportional to mass. So what you understand here is that very bright, very massive stars are typically very bright. Okay, that's what you have to remember. Massive stars are bright. And the second thing is that the star which is basically less mass will be less bright. So this is the thing you have to remember. Okay, so I will just keep it like this. So there are a few things we have been going slightly incrementally. I will connect it in 2 minutes. Okay. So what you use, there is a logic you can follow here. Suppose what we are saying, if the mass is more, it emits more light. Okay. What do you mean by something emitting more light? Emitting more light means a lot of energy is being removed out of the star per unit time faster. If the mass is high, a lot of energy is removed out of the star. So if you are going to remove a lot of money from somebody, the person should have money like that. No? If you want to remove 1 crore from somebody, you cannot take it from a bugger because he doesn't have it. Or you cannot take it from me, I don't have 1 crore. So you have to go to Ambani only, right? This is the logic behind. If you say that more luminosity means that you say that it is emitting more radiation or more energy is lost by this thing. That means this should be the source which is creating more energy. So you can now argue that more energy means more nuclear reaction which is going on. More nuclear reaction means for some reason I am converting hydrogen to helium much more faster compared to what I am doing in low mass stars. That means in high mass stars, I should do it faster compared to low mass stars. Okay. So you can just do a simple calculation. What is the luminosity? Luminosity is nothing but energy per unit time. In this case, what is energy? Energy means I have given some mass. I'm going to convert that mass into energy. So what is the relationship between mass and energy? Suppose if I have m is the mass of gas which is available to me, mass of hydrogen gas, energy available to me is mc square. Okay? mc square is energy available to me. But we know that we don't burn the whole star in nuclear reaction. You will burn only a small fraction of mass which is in the star in the interior, you will burn them. That fraction is F. Suppose if I take F as the fraction, So if I put F as a fraction of mass which is going through the nuclear reaction, what is the maximum energy I will get during its lifetime? Lifetime is what mc square is the energy. Fmc square is what I am having to burn it, and I am going to burn it over a time scale TMS. TMS means how much time the star will live in the main sequence. Okay. So what will be the luminosity? For the purpose of understanding, we assume that I know total energy, I know what is the total time, divide one by another, you will give energy per unit time. So L will go as Fmc square by TMS. So you follow this, a very simple logic. And anyway, my colleagues will explain to you in better detail and give you, because I am giving you an introductory level. I will try to get the thing which you will get after 2-3 hours in 5 minutes. Okay, so that's the, so you follow this now. So now I have the relationship between L and M. I can just convert that relationship between, since I have a relationship between L and T, I can get a relationship between T and M. So what I get, lifetime of a typical lifetime of a star which is going through hydrogen bonding, which means that how long the star will remain in that straight line, which we said, because if hydrogen burning is over, it will start moving. It's like after I pay my toll, or after I pass through the toll which fast track, then I am free. You can't locate me. Now I can go 30 km per hour, 120 km per hour, so you cannot tell where I am. But you can locate me till I am going to pay, because I will be close to the toll booth. This is the analogy, it's a very good analogy to remember. So if you say that how long you will be in the main sequence, that will be inversely proportional to mass to the power 3, right? That means if you are a very massive star, you don't live in the main sequence. You will disappear very quickly. If you are a less mass star like Sun will be shining exactly like this for billions of years. So don't worry, we are not going to be affected by stellar evolution of Sun. So you understood this. This is a very important point. There are a couple of points I have told you. So this will come back again. This is what we said main sequence. Main sequence means the stars will remain with a scaling relation. And you can also see it goes and turns like this. So the way we identify where the curve is turning, our understanding is that this is when your burning of hydrogen stops and you go back to burning, burning helium for nuclear reaction. Once you go there, you deviate from this line. Okay, that is the first thing you have to remember. So this is the line where stars will be looking placed when they are doing hydrogen burning. When the hydrogen burning stops, they will move away from this. How they are moving away, I will not explain. That's not important for me or what we are at it. And you can clearly see, since it is like this, the turning point will have dependence on, you can find out what is the luminosity of the turning point. And luminosity is related to mass. Mass and time are related. So what we have to do is that we are all clever people. We understand everything which is happening here. Suppose this is my luminosity, this is my color, and I start with something like this. I start like this. This is at high. This point is at high luminosity. Then what kind of star will be there at that point? Massive stars. What kind of stars will be here? This will be less massive stars. This is for some time. I wait for some time, right? I just go and have coffee. It means like in cosmic coffee, these time scales are 10 to the 7, 10 to the 8 kind of thing. To come back, what should have happened? Some of these stars would have now disappeared into some other star because they finished burning hydrogen. So this part will be removed. So they will go somewhere. We don't know where they are going. But if I ask you where is the edge of this straight line, you will find that in the beginning it was here. Now it will be here. You understand? That means if I go now and look at the luminosity of the star, brightest star will be the most massive star there. But this will not be the most massive star in the full part because some of the massive stars are not in this line. Okay? So now you can, given this relationship, okay, I'm struggling with, given this relationship, what is the dependence of time and mass? What is the dependence of luminosity and mass? I can do one thing. I can go and look at this curve. if I find that there is a turning point here, I can figure out what is the brightest star there and what is the mass of that star. And since I know mass and lifetime, I can calculate what is the lifetime of the star cluster itself, with the assumption that when I form this cluster, all the stars will start with burning hydrogen. The sequence they will follow. That means it would have been a straight line. After some time, some of the brighter stars have disappeared. Now I know where is the turning point. Given the relationship between mass, luminosity, and time, I can calculate what should be the time so that this cluster will have turning point at a particular luminosity. Okay? Then you can say what is the age of the cluster. So you understood. Now we are doing all sorts of things. We are measuring age of the cluster through a physical process where we understand this is binding on a physical process called hydrogen burning stage. So now you can understand the way we are connecting this. Okay, so this is an example. So this is actually a real globular cluster. This is a cluster of stars where you can find where the turning point is, and you can measure the age by locating the turning point, where exactly the turning point occurs. Okay, what kind of mass and what kind of luminosity is that? So it's why am I jumping from time to this? Because you will figure out. So now, once this, how much time I have? Okay. Once you move out of the hydrogen burning, so hydrogen burning things are, of course, you people are very nice and very obedient, so you didn't ask me anything. You know, if I put a bomb, even fission, somewhere in Bangalore or maybe nearby countries, wherever, you will have earthquake here, right? Means like the effect of any nuclear reaction is so huge. Why the whole star didn't burst into? Why can't it burst and go away? It doesn't happen like that, right? The star is intact, while the nuclear burning is still going on. That is because star has enough mass, and you have an equilibrium where whatever amount of force this nuclear reaction creates to push particle outwards is compensated by the gravity themselves. This is the steady state. When steady reaction is going on, it will remain like this, and this goes by the name called hydrostatic equilibrium in physics, and you will hear about it in coming lectures. What is hydrostatic equilibrium? But imagine this is going on like this. I told very casually, I stop burning hydrogen. I stop hydrogen, and then it goes into helium burning. You didn't ask me any question. You accepted because you are still in college, and we are told that you should not ask any tricky question. Now I will ask you a question. Since you don't ask me a question, I will ask you a question. If I say, if I want to bring two hydrogen atoms to fuse, I am saying it is difficult to start with. I am telling you that after hydrogen is finished, I will bring two helium to fuse with each other. Is it difficult or easy? Because helium is more massive. If I want to bring two nucleus as close as possible to each other so that they will start fusing with each other, I have to really break a strong electrostatic potential compared to what I have done with hydrogen. Agree? So it is going to be more difficult. So will it be natural? Suppose I finish hydrogen burning, what will happen to the star? So suddenly something was pushing outside, gravity was pulling inside. Suddenly whatever is pushing outside is stopped. So what will happen to the star? Star will implode. Star will implode. And this implosion is absolutely essential because it does two things. The temperature will go up in the center. Mean separation between particles will go up. So temperature going up means average velocity of the particle will go up. And if the density of the particles are more, they will interact more. So a crowded place, you will interact with people more compared to an isolated place. Same logic. So clearly, whenever you go from burning of one fuel to another fuel, this kind of jerkiness will happen. But if you settle down to another equilibrium where you are having helium and this gravity compensating, it is okay. The problem is if the burning of helium is very efficient. Suppose you say that if I put two helium atoms, I can burn them very quickly. If you think of such a situation, then you end up with the problem is that before the gas fall or adjust, your fuel will be over. So the equilibrium will keep changing. So this is a very interesting problem. So I have given you the motivation behind studying stars. So this is what will take stars into all sorts of regions. Star will become big, star will become small. And so they move in this color luminosity relations. But there is one set of important problem I can tell you. This is all violently happening. In one particular regime, you will find some interesting physics can happen. The physics is like this. Suppose you have the central region is creating radiation. This radiation goes and interacts with gas in the outer region and leaves. So it can happen in particular set of objects. The radiation coming from inside can be very strong. What it will do is that it will keep traveling outwards. If the outer part is very cold, you have studied something known as Kirchhoff's law. Remember? If a material is at low temperature and if radiation goes through that material, what will happen? It will absorb the radiation. So you can see a situation where if outer regions are cold, the radiation coming from inside will get absorbed by the gas. So you will say, okay, fine, good. But the problem with all these things is that the radiation carries what? It carries energy. Each photon carries two important quantities. One is called energy, another is called momentum. What momentum will do? Momentum will give a force. So if you imagine, I have a star. So imagine this is my star, and I consider an outer region which is pretty cold. Outer ring which is cold, just for our this thing, right? All photons coming from here getting absorbed, and they carry absorption means they heat up the gas. The momentum means they will push them out. So what will happen? They will go out. They try to expand. So absorption of photon by this material will make this guy go out. Okay, you understand that? So your star will keep expanding. So what happens to the luminosity of the star? You can see what happens to the luminosity. If you assume this to be a black body, luminosity is what? Sigma t to the power 4 times 4 pi r square. Sigma t to the power 4 is because it is a Stefan-Boltzmann relation. The black body, if you assume it's radiating like a black body, and you will see that if the guy becomes bigger, or if the star becomes bigger, and assume that the temperature falls slightly, but it becomes bigger, you will see that the luminosity will go because R square dependence is there and L is there. So you can see that your star can become bigger because of the radiation pressure. The problem is when you become bigger, what happens to the density? Density goes down. So you start with some shape like this, you become bigger, bigger, bigger. At some stage, the density becomes so low, your ability to absorb photon goes out. That means these photons, which were originally absorbed, which is pushing this layer outwards, when the layer goes up to some radius, you will find that the density is so low, these photons will just go through them. So what happens then? There is no absorption. When there is no absorption, there is no force. So what happened to this layer? Now gravity will pull them down. So when the area changes, this luminosity will change now, because my R square is changing, t to the power 4 is changing. So you can imagine this very nice physics going on. If you start with the composition of the star can go to some radius and come back. Okay? So what will happen to the light? Light will not be constant, light will go up and down, up and down. So this is what is known as variable stars. It is one kind of variables. These are called periodic variables. You can also have variables because one star will come and shield another star. That is one way of looking at variable stars. Here probably what happens is that you understood this. So these are known as Cepheid variables. Cepheid variables, the physics operation is like this. To get this physics working, the outer atmosphere should be not very hot. If it is very hot, all photons will go. There is no radiation pressure to make it bigger. So if you go to these stars called Cepheid, they have this correct physical condition where they can oscillate like this. So when they are closer to them, they absorb photons, they become big, come back. And you can imagine, since it is governed by the physics of absorption and radiation pressure, the inner radius and outer radius up to which they will go is precisely fixed. There is nothing which is changing. The luminosity range is precisely fixed. So people can now, what you can do is that you can take snippets of different luminosities and plot against the period. So if you see things are going like this, if time versus luminosity, you will find goes like this. I can calculate the period. What is found is that the period luminosity relation, the brighter stars, brighter the star, they oscillate bigger compared to the period is longer compared to the fainter star. Faint and brightness also has to be limited to that range where the outer part can absorb. So this you remember, it's not very large. You see, it's not a very large range one is talking about. But the most important problem is period over which light changes. Will it change with the distance? Suppose I am sending some sine wave from a star, sine waves with pulses. Will it change with the distance? No other relative motion. I keep it at different distances. Will the period change? No, right? But what about luminosity? Luminosity will change because flux is changing. Luminosity is not changing. Flux I receive is changing. So what you can do, if this curve is given to you, if you find something is oscillating periodically, what you can do, you find the period, go to this curve, oh, this is my period. What is my luminosity? You know the luminosity. But you don't measure luminosity, what you measure is flux. So what you can get is distance. So to get a distance of Seifert variables, you don't have to actually worry about anything, you just have to measure the periods. And you understand why this distance estimate is reliable. This distance estimate is reliable because it is governed by a simple physical principle, what is known as opacity. I am using a word opacity. Opacity is related to your ability to absorb photons. This is just related to the modulation in absorption properties of the outer part of the gas. Okay. So, which means now I go back to distances. We start with the radar. Then we start with Kepler motion and measure distances to all planets. Then we have this triangulation. Imagine when you are doing this triangulation, if one of the star which you are doing triangulation and measuring is Seifert variable, you can do this exercise because you have the independent measure of distance. You can measure the distance of the star by using triangulation. You measure the period using its period from the light curves. I mean, like plot time versus intensity, and you get that period. Okay. So now this is the link. You start with Venus. Venus, you connect to Earth distance. Earth, you connect to star distance through triangulation. And in among the star, you pick Seifert variables. There the distances are measured through this. But now period is, you find that there is a period relation. Now you can take Seifert variables from anywhere because you have calibrated this. You can take it from anywhere, not necessarily that 1,20,000 stars which you measured with angles. You can take it from anywhere, even from nearby galaxies. You can take it from nearby galaxies. Then you can measure distances very accurately. This is what is known as distance ladder. Now, if I am measuring distance of a Cepheid galaxy from some Cepheid variable star in a nearby galaxy, not Cepheid galaxy, a Cepheid variable star in a nearby galaxy, how accurately I can measure the distance will come from how accurately I measure the distance to Venus, how accurately I measure the distance to Earth, and that translates to how accurately I measure distance to these 1,20,000 stars, and small fraction of them are Cepheid variables, okay? And how accurately I measure the period. So it's clearly, it's an error propagation. So your highest precision is required in the laser-based measurements. So that's why it's, you remember your measurements, whatever we are talking about, they are all linked. So now if I tell that distance to some galaxy is something, you know that what all is involved. So now we have understood how to find distance to a star cluster. For example, if you take a star cluster, if there are Cepheid variables in the star cluster, this calibration we were worried, right? How to do this calibration. So I told you again, you people accepted. You say that I can scale. I know the distance to one cluster. I can find the distance to another cluster by matching the main sequence. I adjust up and down. How do you find the distance to the first cluster itself? There, you have to locate these Cepheid variables, and then you they are periodically varying, that gives the distance. Okay, so you have linked all the slides I shown now are linked now. Okay, and we have found the distance to nearby galaxies. How do you do? We have done this. Okay. Then another interesting point which is important for us is that this is the last thing I will say and I will stop. Okay, in the stellar evolution, when the whole thing is going on, and you also know that there is a limit to how far you can go in the nuclear reaction. That depends on stable nuclei. See what happened in hydrogen burning, when you form helium, that helium remains stable. Even though other hydrogens are bombarding and producing more and more helium, this helium doesn't go back to hydrogen helium. Hydrogen, the fission doesn't happen. Okay? So that's how we build nuclear reaction. Nuclear reaction means all the products will be stable. They will not be fragile. So this can go on like this, but when you reach iron, the problem is you cannot go beyond iron. Because iron is the most stable nuclei. That means you reach a situation where you are unable to build in sequence. So at some stage of this nuclear reaction, you will find that when the nuclear reaction stops in the center, when you compress them into higher densities, it is not that you are going to gain a lot more energy and stable nuclear burning. So if you press a lot of them very fast, it's like throwing a ball into or throwing an arrow into this thing. There is a bounce before it actually collapses. So what we do now is that that particular situation, the bounce is so large, you end up with two things. Something happens, the compression is so large, some stable star or some solid object forms in the center, which you will see white dwarfs or neutron stars or black hole. But the outer part will go like mad and it will expand to large distances. Okay? So this is related to, this is what is known as supernova. There are 2-3 kinds of supernova possible. One of the supernova is that if you have white dwarf or something, if matter falls into the surface, you can also create strong nuclear reaction suddenly that will give a burst going again. So there are 2 kinds of supernova you will study. The supernova related to this nuclear reaction on the surface of white dwarf goes by the name supernova 1A. And what people have found is very interesting. Again, the way supernova, what happens is that when this burst happens, the luminosity of this thing, this is time versus luminosity will increase and decay in a particular way. What people found, this curve is invariant. In the sense that wherever you go, whether supernova occur today, supernova occur in some other galaxy, supernova occur in some other place, you will find that the distance, the luminosity versus time, or flux versus time of the supernova, the way the curve behaves, is invariant. Okay? So, which means that there is something we can do about it. This is what is known as supernova blaze calibration. What people found is that, so anyway, I have to do a bit more thing here. Maybe I will stop with this because I have to introduce you some concept of distances. Let me just see what I have, okay? Okay, good. I have 3 slides. Okay, we will do it then in my next class. So that I will introduce few more aspects. Now, what we are aiming is that we are aiming to measure distance to larger, most distant objects. So let me just summarize. You agree that you can measure distance to star in our galaxy within Milky Way itself. We can use the techniques, whatever you said. The nearest galaxy we can measure if some variable star is present. And I am just introducing, which I have not explained, which I will do in the next class. If supernova goes off in individual galaxies, supernova we understood what it is. If it goes off in individual galaxies, it's the way the light will behave with respect to time is invariant. And that can be used to measure distances to this. So I will do this and I will introduce what is Hubble law in the next class so that we will measure distances to very distant galaxies. And then I will close this. Okay. One request, tomorrow my lecture is scheduled around 9:30, but I have an important telecon around 9:15. So I will come 10 minutes late. Please wait for me. I will take class 15 minutes more. But don't disperse saying that this guy is not there or don't complain. I'll come maybe around 940 or something like that. Right. So if you have any questions, I can take now, and then we can discuss.
So why is the peak like that? Supernova.
Actually, peak is expected. Na? When there is no light, suddenly some light comes, it will build up from somewhere. So actually, this part is going and reaching a peak is okay. And how much light is in the peak depends on what fraction of the energy you are extracting. Up to that part is fine. What is more crucial is that what happens to the decay, why the light is decaying. And what happens in supernova is that when supernova explodes, a lot of things happen because you are also pushing gas at high velocity and also pushing gas very close to each other. Because imagine something, it's like sweeping. Huh? You have dust particle all over the place. You are sweeping means you are collecting particles close to that. In fact, you are also giving some energy to them. They will move very fast outside. Since you are pressing particles together at high temperature, you can also produce nuclear fusion during this period. And it is extremely important because here what happens, this is not a stable nuclear reaction like what you see in the center of the star. Center of the star, what happens? There is formation, and because of heat, these particles are also destroyed. And you write an equilibrium and calculate if the formation is faster, then you will keep accumulating this. Here, what happens? You have a situation where nuclear reactions can take place, but they are not in equilibrium. So which means that if you form, this is very useful for elements which are heavier than iron or something. Here, there is a correct physical situation to form elements which are brighter than iron because you can fuse them together with high energy. But the density is so low, they are not going to be breaking into it. That's what happens in the high density environment. When you create any nuclei which is heavier than iron, it can break into smaller nuclei. Here it will not happen. So this is rapid buildup of elements is possible whenever there is a explosion like this. So when you create elements, you will create elements with different kinds of isotopes. And what is the thing we know about isotopes? There are stable isotopes and unstable isotopes, right? Unstable isotopes mean they will decay. So this part is related to what kind of isotopes you are creating. And these isotopes depend on whatever is in the surface of the neutron stars. And you create these isotopes. When isotope decay means they will radiate. No? So this radiation pattern is well documented. That's why this part is very interesting. So they fix it like this. So again, why supernova is special for supernova 1A is special is that it is related to this, related to the fact that you create nuclear reaction in an open space and you are going to create nucleons which are isotopes, and the isotopic decay is what you are capturing. In fact, if whatever I'm saying is correct, if you go and take the spectrum, you will see this decay will occur at certain lines, right? You can detect them. You can detect the ions, cobalt, nickel. These are created. In fact, you would have heard now when people discovered gravitational wave in 2017, they also discovered gold. So they say that this is the proof of what is it called? R process going on, R process nucleosynthesis going on in space. So they said, no, gold we are detecting. They detected signatures of this. So such heavier elements are created like this. The physics is, if the physics is just like expanding, you will say that why should the expansion be symmetric? Why can't it be asymmetric? Then there is various things will come. So the curve cannot be stable. But if I say that if I give what you call isotope, and you know that the isotopic decay timescale is decided by quantum mechanics. So it is fixed. So all the elements, all the physics we use to measure distances, they have to be governed by single physics, which is most trustworthy. So in this particular case, it was a good question. I would have taught as a part of what you call stellar structure evolution. Maybe I was thinking of doing it tomorrow. Going up is okay, that you know, it has to go up. There should be no light when supernova comes, light should go up. So this you are not very much worried. How bright it can go is also you will know like it's proportional to how much burning has happened. But the slope of this particular curve depends on the decay of, there is a time scale over which different element will decay, If they decay, that emission will go away. So this can be predicted from basic physics. Any other question?
Sir, what are the kinds of supernova explosions? How we categorize supernova explosions? Like one is how we categorize it? And for each, the light curve will be different. What would the same pattern?
Light curve will be different. Compositions will be different. See, basically, what happened in one case, a supernova appearing in the center, and the gas is going outwards. This is actually, if supernova 2, there is a core which is there, and that is bursting the whole gas around that envelope. Whereas in the supernova 1A, you have white dwarf. What is white dwarf? White dwarf is basically like a electron matter, right? You can think of like a dense electron matter. It doesn't emit anything. There is no nuclear reaction. It is just a compact object held by its gravity. Okay. If I put some gas on top with sufficient necessary conditions, you can create surface nuclear reaction. So type 1A and type 2 are different. One is the nuclear reaction in the central region. Here it is a surface nuclear reaction. And what are the ingredients you will have? Whatever is in the surface is the one plus the gas which is falling. They will be participating in the nuclear reaction. So if you look at the white dwarfs, you will have all these elements: magnesium, aluminum. These are in the surface. So they are not hydrogen. So that's why when surface nuclear reaction happens, the composition will tell you which kind of. If you can take spectrum, you can tell clearly which kind of supernova you are dealing with. And the light curve will not be same. I think whatever physics I explained to you, that will be the light curve for supernova 1A. Whereas in the case of supernova 2, it is expansion. Gas expanding, because the area is going up, temperature is going down, that will give rise to sun.
So it will not be a question.
It is not Gaussian. It just rises and falls with something. It decay, na? You would have, you know how isotopic decay? Exponential something, right? Anything else?
So, sir, all these reactions, they are uniform all over the surface, or is there any difference going on at all?
No. The idea is that they will spread. They will spread in the surface. So it's in, okay. For the time being, you will then ask me how do they spread? Then I have to explain to you how the gas fall in the first place. So this happens when they are in binaries. Gas goes from one to the other, and since they are going around, you will typically see that even if you ignite nuclear reaction in one place, it will spread across. So it will happen in the most of the surface.
So if we take a single star only where each asking about all this reaction of hydrogen going to helium and all that. So are they uniform all over the surface, or there is some difference going on at the pool because of the difference in the.
Typically, they are uniform. Uniform means like you have to also tell me what is the meaning of uniform. There is nothing uniform now. You will say that, suppose if I say, okay, now it's interesting. Now you just say, I say it is a straight line. Straight line up to some accuracy, right? Is it a straight line at 1 part in 10 to the 4? No, because I draw with my hand. If I take 2 points, the straight line means you will have a slope, well-defined slope. But even if I say a horizontal line, the slope should be 0. But will it be that way? No. So again, whether it is uniform or not, you have to say in what. Suppose you say that if the star is a sphere, that means the radius you can measure in all directions, you will find something. It will be sphere up to some accuracy. Now. If you say that the radius is 10 kilometers and the uncertainty is 5 kilometers, will you be worried? You will be worried because this is like going like this. Suppose the radius is 10 kilometers, accuracy is 100 meters. You will say it is sphere, no? More or less sphere. So it's a sphere in 1 part in some fact. So always physics, there is no precise measurement. Your acceptance is related to the tolerance with you. I'll stop. Anyway.
Anand, there are a couple of questions on the chat.
Yeah. No, see, there is a question says, is there distance limit to Seifert variable? No. You can measure it. How long does secret variable last? It lasts much longer than our lifetime, so we don't have to worry. Okay, I will suggest reference book in the next class. Is there anything else? I explained supernova standard candle. I said I will do it tomorrow again. Okay. Okay, so that written on the board visible. Okay, that you have to do. They said that whenever
Yeah,
you have
we'll
to.
take care.
Okay, that's all I think. Okay, I'll
Yeah.
stop.
Thanks.
You can go for tea and come back.